So in our first lesson, lesson number 1 of equation solving, we looked at simply taking an answer that was given to us, plugging it in, and seeing if it made the equation true or not. Is it a solution or not? Does it make the left side equal the right side? If it does, then yes, it's a solution. If it doesn't, then no, it's not. So now we're going to actually start to solve some really simple equations, and I'm going to re-emphasize that even though the equations we're going to do at the start are easy enough that you'll just be able to look at them and know the answer most of the time, like this one here, x is 5. Remember, we're working towards equations like this that we won't be able to look at and know the answer. We need techniques to approach these ones, and we're going to figure those techniques out by looking at really simple ones. So don't just say, well, I can tell it's 5. I don't need to listen to the rest of it. You need to listen to the approach that we will be taking for all the equations, no matter how complicated they get. So we're going to start with simple ones, develop techniques that we can apply to more complicated ones. This is everything I just said already. I forgot I had it written on a slide. I won't say it again. Learn the techniques on the simple ones to apply to the tricky ones. Okay, so first thing we're going to remember here, that an equal sign simply means that whatever's on the left is equal to whatever's on the right. So there's a really simple example. 5 plus 3 is equal to 8. The thing on the left is equal to the thing on the right. Normally in math, we can't just change things in arbitrary ways. So this is I think I gave an example of this during the break, but if the question says that the road is 40 kilometers long, you can't just say, yeah, I'm going to add 3 to that, and I'm going to make the road 43 kilometers long for this question. You'll get it wrong, right? You can't just change things. But as soon as you have an equation, we have a superpower. We can change anything we want as long as we do the exact same thing to both sides, so they're still equal to each other. So let's see, I forget what I do here. We know that 5 plus 3 is 8. So I'm going to add 7 to both sides that I've done in red there. And let's just sort of look sort of halfway down how that works out. 7 plus 5 is 12. 7 plus 8 on the right is 15. So this becomes now 12 plus 3 is equal to 15. That is still a true statement, right? So it's not the same. Is 8 equal to 15? No, I changed it, but I changed the other side of the equation in the exact same way so that they're still equal. Or let's say randomly that I'm going to multiply both sides of the equation by 4. Now we know that 4 on the left goes through the bracket, so it's 4 times 5 plus 4 times 3. And then on the right, 4 times 8. Look what we get. 20 plus 12 equals 32. So once again, 8 is not equal to 32. 3 is not equal to 12, and 5 is not equal to 20, right? Everything is changed, but because I changed the left and the right side of the equation in exactly the same way, I still have something that is true. 20 plus 12 is equal to 32. So I start with something that is true. 5 plus 3 is 8. I change both sides in the same way, and I end up with something that is still true. And so equation solving is basically choosing the way you're going to change both sides so that you can slowly make the equation simpler and simpler until you can solve it. So the goal in equation solving is, the technical words is isolate the variable. All that means is that we want to get the variable by itself on one side of the equal sign. So to do this, we are going to make use of the fact that we can do anything we want as long as we do it to both sides. And that means that we can do things that will make the stuff that's with the variable go away. So you want to get the x all by itself, but right now there's a 2 with it. We want to make that 2 go away. We're going to do something that makes that 2 go away, and then we're going to do it to both sides of the equation because we're allowed to do that. So for example, here's our equation, x plus 3 equals 8. We already know, we can just tell the answer is 5, but we're going to pretend we can't. Yeah, easy to see the answer is 5, but what if it was a harder one where we couldn't just see the answer? What is making the x not be isolated? Why is the x not by itself? There's the equal sign. And here, this question, these two questions are what you're going to ask yourself over and over and over and over whenever you're solving equations. Is the x by itself? No. What's making it not be by itself? A plus 3. What is the opposite of a plus 3? The opposite of a plus 3, of adding 3, is subtracting 3. So I am going to, and I really would have wanted to put those in red, I think. I think PowerPoint's doing its weird thing where it takes out my colors when I make changes in later slides. Right? I can do anything I want as long as I do it to both sides of the equation. So I do something that will make the plus 3 disappear, a minus 3. So what happens on the left? X plus 3 minus 3. The plus 3 minus 3 goes away. So all that's left on the left side of the equation is just an x, which is exactly what we want. Over on the right side of the equation, we get our answer 5. Yes, we already knew that was the answer because it's a simple question, but this helped us learn the strategy. Do something that will make the plus 3 go away, and then do it to both sides. So here's those questions we were just talking about. Is the variable by itself yet on one side of the equal sign? If no, what is still with it? Make that thing go away by using what's called the inverse operation. That's just fancy math words for the thing that makes it go away. Really, honestly, that's what it means. So p minus 7 equals 15, 3t equals 0. So we got 3 equations here, and we're going to ask those questions for all of these. So for the first equation, is the p by itself? Oops, I got ahead of myself. Oh, it's taken out all my colors. I'm so upset. Is the p by itself? No, because there's that there with it, right? What's still with it? A minus 7. What is the opposite of minus 7? The opposite of minus 7, if it's taken all my colors through the whole thing, I'm going to be really ticked, is plus 7. So I do that thing to both sides of the equation because it makes, on the left side of the equation, minus 7 plus 7 just goes away, and all that's left on the left side of the equation is a p, and the plus 7 appears over there on the right. And I would like you to notice this. Oh, I do not know why this happened. There. So I would like you to just to notice and sort of store away in the back of your mind that the effect of this was when you're adding or subtracting something, here we're subtracting 7 on the left. Look what the effect of adding these 7s to both sides was. It kind of looks like the minus 7 on the left became a plus 7 on the right. That did happen, but always in the back of your mind, you want to remember why it happened, because you added 7 to both sides. This one canceled out, that one stayed there. But once you get good at equation solving, you don't think that through every time. You just see that subtracted 7 on the left becomes an added 7 on the right because of what we did to both sides. 15 plus 7 is 22, and there's our answer. Let's look at this next one, 3t equals 14. Oops. Ask the question, is the variable by itself? Is the t by itself? No, it's not. There's that 3 with it. How is that 3 connected? That 3 is not added. It's not subtracted. That 3 is multiplied by the t. What makes times 3 go away? What's the opposite of times 3? It is divided by 3. So we divide both sides by 3. And once again, times 3 divided by 3, those just cancel out. Times 3 divided by 3 is 1, right? Doesn't do anything. And 14 over 3, don't panic. We don't mind fraction answers. 14 over 3, read the instructions. Do they want an improper fraction? Or do they want a mixed number, 4 2/3? Or sometimes, as we just saw in that other example between lessons, sometimes they want a decimal, in which case you punch that into your calculator, 14 divided by 3. I would like you to notice here that, remember how we talked before about how the minus 7 on the left became a plus 7 on the right? Some people see that and they overextend that idea. And they think that this plus 3 on the left becomes a minus 3 on the right, but it doesn't. Why did this minus 7 become a plus 7? Because I added 7 to both sides. I added 7 makes that plus 7 appear on the right. Here, I didn't add 7. I didn't add 3. I divided by 3 on both sides. That 3 doesn't magically become a negative 3, right? I added 7 to both sides. It makes it look like a minus 7 on the left became a plus 7 on the right. Here, I just divided both sides by 3, and then I turned my answer into a fraction answer. Last one, is the h by itself? No, it's not, because there's something with it on its side of the equation. What is with it? A divided by 5. What makes dividing by 5 go away? Multiplying by 5. So I multiply both sides by 5. And these 5s cancel out. Now, if you don't like that, let me show you one more little step here that we could technically include. That 5 is actually 5 over 1. And then when you do the fraction work, you can see the 5 on the top and bottom cancels out, right? So the left side, the 5s cancel out, you're just left with an h. The right side, 15 times 5 is 75. There's the basic idea. And we're going to do a few more. I'm just trying to think, was I going to get you to try these ones? No, I think we're going to just carry on and see a few more examples. So, is the v by itself on its side of the equal sign? No, it's not. What is with it? A plus 13, adding 13. What is the opposite of adding 13? Subtracting 13. Like so. So I subtract 13 from both sides. Why? Because it makes on the left plus 13 minus 13 just disappears, and all that remains on the left is a v. Over on the right, negative 42 minus 13. And I would like you to notice once again this handy little thing that we're eventually going to start to use, that a 13 that was added on the left ends up being a 13 being subtracted on the right. Why? Because I subtracted 13 from both sides. So what we're going to eventually start to do is we're going to skip this step that I'm showing there with the red. When we're adding and subtracting, we're just going to say, that plus 13 on the left will become a minus 13 on the right. And then work out your answer. Negative, careful with your negatives and positives. Negative 42 is going to the left. Negative 13 is also going to the left, so we go further to the left. 42 plus 13 is 55 negative because we're going left. Okay, so on to the next one. Is the n by itself? No. What's with it? It's being multiplied by negative 7, right? There's not a 7 being subtracted, so we're not going to add 7 to both sides. That 7 is not connected to the n by subtraction. That negative 7 is connected by multiplication. What's the opposite of multiplying? Dividing. So I divide both sides by negative 7. Right? So don't get fooled with that negative sign thinking that that's a plus. It's all about how the things are connected, right? This 13 is being added. This 16 over here is being subtracted from the c, so we will add that 16 when we get there. This negative 7 is being multiplied, so we do the opposite, always the opposite. be plus 13, adding 13, we subtract 13. Subtracting 16, we will add 16. Multiplying by negative 7, we will divide by negative 7. That makes that the negative 7s cancel out, so we're simply left with 42 over negative 7. Again, notice it did not magically become a plus 7, right? Because it did not get over here by adding it to both sides. It got over here by dividing by negative 7 on both sides. And we get an answer of 42 over 7 is 6. A positive divided by a negative is a negative. And then the last one is the c by itself on one side of the equal sign. No, because there is a 16 being subtracted from it. What makes a subtracted 16 go away? Adding 16, and again my colors have all disappeared. Not that it really matters, but I find that just helps students see it. But as we were just talking about with that last question, once you get good at this, you will start skipping this step, right? And you will start going straight to the fact that a minus 16 on the left, a subtracted 16, right? Subtracted specifically, becomes an added 16 on the right, like so. But in the back of your mind somewhere, you never forget the only reason that works is because what you technically just did is you changed both sides in the same way by adding 16 to both sides. Negative 9, so 9 to the left, 16 to the right, so they're moving in opposite directions, so we subtract them. 16 minus 9 is 7. Which one is bigger? We went further to the right, so our answer is positive. That's a good little review for those of you still working through chapter 1 with your adding and subtracting integers in the review chapter. Okay, here I think I plan to describe exactly what we just went through. Yeah, so here, and I put the different colors just showing that negative 7 being multiplied doesn't switch signs. When we have a fraction multiplied by the variable, there are a few options for how to do this. So I'm going to show you all three. They all work, but I'm going to suggest that one of them is far, far easier than the others. So one option is we can just do the same thing we did on all the other ones. You can say, what's with that d? There's a 2/3 being multiplied by it, right? And so we could divide both sides by 2/3. You can see already this method is looking pretty ugly. Over on the left, the 2/3 and the 2/3 will cancel because they're being multiplied and divided. Or if you want to do fraction division is multiplication by the reciprocal, you will see why that works. Over on the right, 12 divided by 2/3 is 12 over 1 divided by 2 over 3. We got to make everything fractions. Division turns into multiplying by the reciprocal, right? That's our division rule. So you can see, again, this method gets pretty ugly. I'm going to do a little canceling there with the 12 and the 2 because they both divide by 2, so it becomes 6 and 1. 6 times 3 on the top is 18. 1 times 1 on the bottom is 1. Of course, we would never write 18 over 1. We would just write 18. So that is one option. I would suggest that's the worst option of what we're going to look at here, dividing by both sides by that fraction. Option 2 is we're going to multiply by 3 over 2. Now, I want you to pause right now for a moment and look at option 1 and option 2 and realize that they literally say the same thing. Divide by 2/3. What does dividing by 2/3 mean? It means multiplying by 3 over 2, right? Dividing by a fraction is multiplying by the reciprocal. So option 2 is literally saying the same thing as option 1, but we're not going to end up with all this big mess here. So let's try this. I have d being multiplied by 2/3, and I want to make that go away. So I multiply by 3 over 2 on both sides. And you can see in red, I did the same thing to both sides of the equation, so this is legal. Look at how nicely this works out. On the left, we get 6 over 6. which is just 1, right? The 6's cancel. On the right, we still have to do our fraction work. So turn the 12 into 12 over 1. Do your canceling like we did before. And there's your answer, 18 as well. Much less work. So when you're faced with, if you're tempted to divide by a fraction, instead multiply by the reciprocal. Will be much easier. Option 3, I almost hesitate to do, but let's do it very quickly here. Option 3 is I could make the denominator of the fraction go away first, and then it just becomes a simple question. So I could say, ooh, I don't like that fraction. I don't like the 3 there. Let's just make it go away by multiplying both sides by 3. Like so. Okay. So now what will happen on the left there? That 3 becomes a 3 over 1. And now you can see the 3's just cancel right out. So all the fractions go away, and you're simply left with 2d. This is a technique that we'll come back to when we get to more complicated equations with fractions in them. We'll use our superpower of being able to do anything we want to an equation, as long as we do it to both sides, to take a step and make all the fractions just disappear so we don't even need to worry about them. That's why it's worth showing you this here. So I multiplied by 3, which made the 3's go away. All that's left is 2 times d. And on the right, 3 times 12 is 36. Divide both sides by 2 to make the times 2 go away. And d equals 18. 3 different methods. I think the middle one's the easiest, although the right one is probably the most versatile in terms of other types of situations you're going to run into. Why don't you try these ones here? I've got a few, and we'll take I'll give you 5 minutes till 7:09 or so, and see if you can, how far you can get on these. So by using opposite operations, right? Use the opposite of adding is subtracting, the opposite of multiplying is dividing, to get the variables by themselves. Okay, I think that's probably good. And there, I just worked them all out quickly there. So you should have got answers of -5, 7 over 2, or 3.5, or 30 and 35. And I guess we could just very quickly talk through what happened here. We had an 18 being subtracted, and so I added an 18. By the way, you might notice I'm very intentionally saying an 18 being subtracted instead of a -18. Because here you could say I have a -12, but that -12 is being multiplied, right? So you get rid of it with division. So look at this, and don't just say it's a -18. Say that 18 is being subtracted. Get rid of subtraction with, and again the colors have gone out, but with addition, like so. And if you're good, once you get good at this, you will skip that middle step as we've been talking about. You will realize that an 18 being subtracted on the left ends up simply becoming an 18 being added on the right. And so skip the middle step, go to here and get your answer. Second one, there was a -12 being multiplied, so I divided both sides by -12. And the negatives cancel, right? Negative over a negative, negatives being divided becomes a positive, and the fractions reduce because 6 goes into top and bottom, giving you 42 divided by 6 is 7, over 12 divided by 6 is 2. Read the question to see if they want an improper fraction or a mixed number or a decimal. And then the last one, we had a 3/5 being multiplied, so I realized the quick way to make that go away is by multiplying by 5/3. Am I allowed to multiply by 5/3? Sure I am, as long as I do it to both sides. Whenever you have fraction work come up, like 5/3 times 21, make sure you turn that 21 into a fraction, 21 over 1.